Welcome to DataMites family. In today's video, we'll be seeing about one of the transformation techniques called Box Cox Transformation. In Box Cox Transformation is a powerful transformation technique used to stabilize variance and make data more normally distributed. And this particular point being the most common for all the transformation technique. So the ultimate purpose is to stabilize the variance and make data more normally distributed. It is a flexible and widely used method for transforming data that is skewed or has no constant variance. Why use Box Cox transformation? So I have listed out a bunch of reasons. One, let's say you have a skewed data, and by applying Box Cox transformation, it can help to reduce the skewness in the data, so making it more symmetric. If it is more symmetric, easier to work with, so thereby it will increase the machine learning accuracy as well. And non-constant variance. Whenever there is non-constant variance, this Box Cox transformation helps in stabilizing that variance, making it more consistent, and easier to the model. Non-normal data. Whenever you have non-normal distribution of the data, it will help to convert it into a more normally distributed, not the exact, more likely into a normal distributed data. So this is to transform the normal data into normal distribution. So this is the formula. So if lambda is not equal to 0, then y to the power lambda minus 1 by lambda. If lambda is exactly equals to 0, then log y is applied. A logarithmic transformation is applied, where y is the original data and lambda is a parameter that determines the transformation. Purpose, as we have discussed, one, to stabilize the variance, improve normality, enhance interpretability. When to use it? When we have a skewed data or it has a lot of outliers. Second situation is when assumption of normality is critical for statistical methods. Example in case of linear regression. And data exhibiting exponential growth pattern. We go ahead with Box Cox transformation. Effect of transformation. So in this Box Cox transformation, it will help us in normalizing the data. So transforming the data into a normal distribution, and it also helps in stabilizing the variance. The applications of it being statistical analysis for regression analysis, ANOVA and other tests as well, and for process improvement. So any process can be defined by a Lean Six Sigma rule. Okay, so it helps us in improving that part. Limitations being lambda is not close to 1. Okay, the transform data may be harder to interpret when the lambda is close to 1. If it is close to 1, what happens? Let's see in the next slide. Okay, but what is not desirable is we don't want lambda close to 1 if in case you want to apply Box Cox transformation. Okay, so in detail we'll be discussing in the next slide. As of now, there is one more limitation, that is data restriction. So what is the biggest restriction I can call it over here is the input data should be positive. It won't take any zero values or negative data in it. Okay, so before undergoing the transformation, the input should be positive. That is one more limitation. So choosing lambda, the optimal value of lambda can be determined using maximum likelihood estimation. Using this method, we'll be calculating the optimal value of lambda. Okay, so we'll be using this package called as sci-fi.stats, in which there is a module. Okay, the method is Box Cox. So as I've told you, lambda 1. If it is close to 1 or if it is 1, it means that it is already normally distributed. Okay, already normally distributed. If it is already normally distributed, then why would we do any kind of transformation? We don't want to disturb the normal distribution, right? So if it is close to 1, lambda is close to 1, or if it is equals to 1, then transformation may not be necessary. So we don't apply transformation on such data. So let's see the practical implementation part. So here again, I would like to highlight the point. It is applicable to non-negative data. Even if you are getting negative or zero, you have to convert it. So this transformation involves raising the data to a power. What is that power here? Lambda, which we'll be finding out with maximum likelihood estimation. So I'm taking a column from loan amount CSV, column named as loan amount term. So from sci-fi.stats, I have imported Box Cox. In this Box Cox, I'm fitting my column, loan amount term. So let me show you the data. So this is the data, loan amount tenure. So here you can see the loan amount tenure. Let's proceed with our transformation. So by fitting this particular loan amount term column into the Box Cox, we can see we have transformed the data. This particular output, I'll be storing it in two variables or two identifiers, the transformed data lambda value. So if I go ahead and print the transformed data, this is our transformed data. So each and every data point, as the formula which I have shown you, the formula got applied on each and every data point, and lambda at the back end got calculated, and this is our transformed data. And this is our lambda value. If lambda value is 1, again, it means already it is normally distributed. So here, the lambda value is 3, which is a good thing. It is close to 1. So this is the Box Cox transformation. If you try to plot the graph, you'll be getting a graph which is something very likely or very close to a normal distributed graph. So thank you for watching the video.